Good morning. My name is Shantanu Godbole, and I'm so happy to have you here. Today, I'll take this opportunity to discuss how natural language processing evolved from classical NLP to deep learning to transformers like BERT and GPT-3. I'm sure we have heard about that and amazing things that transformer models are able to achieve. So to dive deep into that, in my opinion, on how the transformers and the architecture works, I have prepared this presentation to walk through the journey or to just get a glimpse of the journey on how NLP has evolved till today's modern day NLP from classical NLP. Long before neural networks were introduced in natural language processing, practitioners heavily depended on statistical techniques like word similarity. So if in few sentences there are a lot of words repeating, naturally the sentences are going to be similar and can be clustered together. Another technique is TF-IDF, which means a term frequency inverse document frequency. So what TF-IDF does is, in a corpus of documents, if you want to, for example, identify topic of each document, so try to find a word which is most common in that document, but extremely less common in the entire corpus in the other documents. So if we can find a word like that, naturally, or it is more probable that that particular word is topic of the document. Now I'm sure we all have seen word clouds, which, if run on different documents, can give us the repetition of words and can highlight what document is representing in general. Rule-based systems. So, a lot of systems back in those days were written on algorithms, such as if cache words, the word cache, the word gift card, the word award, the word cruise, if it appears so many times in an email, there is likely a chance that that particular email is spam, and so on and so forth. Parts of speech analysis. So parts of speech are noun, verb, adjectives, and so on and so forth. So much before deep learning was introduced, there were heuristical methods to tag the parts of speech, which obviously gave a lot of intuition into what that sentence means. Lemmatization. Lemmatization is tying different words, playing, played, to the root word, which is play, right? So if we can remove the different versions of the root word, and if we are able to point those versions to the root word, we can easily make sense of what that word is. It makes the problem statement less complex, and we can tie it to parts of speech, for example, and then get much more sense out of the document or a sentence. Lexical analysis is tying similar words together. So we all know that one word or different words could mean the same thing. So obviously, if we have a lexicon and if we try to group similar words or similar sentences having a common word based on the lexicon, then we are, obviously potentially getting a lot more sense out of that particular statement. Naive Bayes is, if given a condition, if a condition is met, and so on, there is a chance that that particular sentence or a document belongs to certain category. So, again, checking the repetition of words and sentences in an email using naive Bayes can, give us much more insight if the email is spam or not. Finally, to, one of my favorite topics, which is deep learning in natural language processing. So, when we talk about neural networks, which is other name for deep learning, because when a network has many layers and we go deep into the network, it is called deep learning, right? So we think about neural networks or deep learning as a very new technique, but don't quote me on this if I'm not wrong. It was first conceptualized somewhere in, I think, late 1950s. And the thing is, for back propagation and training and tuning the neural network, it requires immense amount of computational power, right? So, which is abundantly available in past few years. So with the progression in computing power, the GPUs being available parallelly to train the neural network, and the libraries, available in an open source format like PyTorch and TensorFlow, the research on neural network and the application of neural networks actually exponentially grew in last few years. So we all know neural networks have done wonders in natural language processing, and we all have heard about different techniques that we'll dive in further, like word-to-vec, glove, RNNs, LSTMs, and so on and so forth. So, why we call natural language, English for example, natural language, because it is something which has evolved naturally. Nobody has written like rules and regulations for that. For example, a programming language is an artificial language which has strict rules. So to analyze that, we can assume that a language is going to be in certain format with keywords and the syntax repeating in a particular fashion. But it is not the case in natural language, and therefore, in order for a computer to understand natural language, all of us know that humans do very well with natural language, and computers are basically machines that do arithmetic calculations. So, we can say that computers understand numbers in a much better format. So, the main task here using neural networks was to convert language, that is words, to vectors. So vector is an n-dimensional vector, and as we increase the dimensions, definitely the vector is going to carry more information, and it is going to carry more context along with it. And it is obviously going to require more processing power as well. But since processing power is abundantly available now, increasing the vector size is not a huge bottleneck in past few years. So when a neural network application in NLP began, this was really like a brilliant task on converting words to vectors. And how it is done is in a big language corpus. We take the neural network, and given, obviously all the words are one-hot encoded to begin with. So each word has, we can call, n-dimensional unique ID. And then in a given window, we take the adjacent words. So n-1, n-2. So for example, the middle word here is the target, and two previous words and two consequent words are given as input, and this window size can vary as per the design. So two pre-words for the n word and two post words for the n word are given as inputs, and we have to predict the word vector, obviously, using the vectors of those 4 words. So that is the problem statement, that is the neural network, and this is the hidden layer. So the network over and over again with the sliding window across sentences, across documents, tries to predict that particular word, and for this particular word in this instance, the weight of the weights of the hidden layer is nothing but the vector of that particular word. A little difficult to imagine, but I would recommend to read a few more articles on this. You can reach out to me. I have gone through a bunch of videos on YouTube to understand this concept, and it is really a very brilliant concept. So once this training is done across the corpus of all the words, every word will have a unique vector, right? And the beauty of those particular vectors is that the vectors of words with similar meaning will be closer in the vector space. So king and queen will be closer together in the vector space than king and rocket, right? So thus a vector and its cosine difference, cosine distance in between the other word can help to determine how similar meaning wise the words are or how far they are. So this was one of the networks that was used to train that was used to create vectors from words, and it really did wonders. The other very similar model, or rather opposite model, is skipgram. So given the n word, try to predict the words around the particular word. And again, the weights of the hidden layer are is the vector of that particular word. So this neural network will train over corpus and give us the word vectors. Beautiful, isn't it? So glove is something that we put on our hands to keep our hands safe and sanitized. And that is a very crucial practice in natural language processing. I'm just kidding. But there is something called as glove. So let's dive into it on the next slide. Glove is global vectors, and the basic concept is straightforward, that there is a co-occurrence matrix that is maintained over the corpus, and a count is kept on how frequently 2 words appear together. And this is factored into the actual word vectors that we saw. So, there is one more process of bringing similar words together on the basis of their co-occurrence globally in the entire corpus. So, this is nothing but glove. A very interesting concept, and I would really recommend to read the referred article on the blog on towards data science, and it can give you guys much more insights on this. Then came the era of RNNs, and before we dive into this, let's talk about a drawback of previous method. So we know that context of words is important in any natural language, and let's take for example, I am going to the bank and I am going to the river bank. So with word2vec, one word has one vector, right? So when a computer tries to understand both the sentences word by word, bank is going to have same vector in both the cases. So that is not ideal, one. And the second thing is, in natural language, as we are talking, as the words are flowing, the sequence makes a difference or makes a big impact, the sequence of the words you're using, right? So what word is coming after what word does determine a lot of sense out of the statement or a sentence. Okay, so that was kind of lost because in word2vec, probably in the classification, all the vectors were either aggregated or pooled. So the sense of flow was being lost. And then that gave rise to RNNs, where we can technically run the neural network on words, word by word. I, let's assume time step 0, where I'm running the sentence, I am going to the bank. So the let me get the pointer. Okay, I really hope you guys can see this. So I goes in here, there is no previous state, so obviously that is blank. And then I goes in here, runs over whatever neural network which we are training, and then returns a state. Okay, and then that particular state is fed back again in time step number 2, am. So am is going in here, and we have the return state of I pretty much from the previous time step, and then both the states are together fed to the neural network. And then on time step 1, it will be a combination of I and am, and then the combined output of the previous step is fed to the neural network again along with the word going, and so on and so forth. So what this does is retains a perspective on flow of the statement. Okay, and that gave, that was very crucial, and that gave a lot of sense and a lot of maturity to the network in understanding the flow of words. The limitation to this was, as we progressed in long sentences, the meaning of earlier words was getting diluted because of the long sequences. So that gave rise to LSTMs, where there are LSTM means long short-term memory. So basically, there are 4 neural networks in one particular LSTM cell that try to learn from the training step that what needs to be forgotten and what needs to be remembered. And GRU is similar, having 3 neural networks. So I would recommend you guys to check LSTMs and GRUs and RNNs in detail. But, this was a breakthrough in understanding the sequence of the words in any particular paragraph or sentence that made the neural networks really efficient. So again, moving forward, one of the drawbacks of LSTM was that it was overfitting, very easily. So to your problem statement, it did overfit easily on the training data. And then again, we are missing one, one concept here in these networks is per the sequence, whatever sequence the words are, we are paying equal importance to all the words, no matter what. Okay, and that is, kind of sometimes problematic in determining the meaning of the sentence. So, for example, if we are trying to classify using LSTMs that a particular statement is abusive or not, okay, so there is a place, for example, there is a location mentioned in that statement, and that location is not significant from the sense of abusiveness. Only certain words are significant. So attention is equally paid to all of the words in LSTM, and that was causing problems in or efficiency issues in tasks such as translation, and which really gave rise to attention mechanism, which tries to figure out, where to pay more attention by how much. So we'll dive into attention mechanism on the next slide, but I would really recommend everybody to check Elmo. Okay, so Elmo is a language model which is trained on Lstms. And what Elmo does is, if I pass a sentence onto Elmo, Elmo is going to return word vectors for that particular sentence. Okay, so if I pass, again, my favorite example, I am going to the bank, then it is going to return, I'm going to pass the entire sentence, and it is going to return word vectors for each particular word. So if I pass two sentences, I am going to the bank and I am going to the river bank in Elmo, which is based on Lstms. For the word bank, in both the cases, I'll be getting different vectors. So, thus that problem was solved. And, I really recommend you guys to check Elmo out, and that can give you, understanding in what the contextual vectors are. Before we dive into attention, let's talk about the neural network displayed on this particular slide. So this is encoder decoder architecture, and we can see that an RNN is used. So this is like a typical translation task where there is a Russian sentence fed, each word, as we discussed, will be passed over a neural network over the time steps. There will be one final output after all the time steps, and it is the context vector. And then that particular vector is the context is used to decode into English word vectors. So basically, a Russian sentence was compressed, if we can call it, into a context vector. That particular vector was used time step by time step to decode or to get the English words out of the neural network, the English word vectors out from the neural network. So this is like a typical translation task. And like the attention problem we talked about on the previous slide, the context vector right here has all the word information compressed. Okay, maybe while translating at every time step, all the words are not important, right? So then there is this problem of where to pay attention to. And this is a very complicated concept, but I'll try to simplify it just by saying that there is one more layer, which is the attention layer, which trains as we are training the language task, and which gives us softmax values on what words are important at what particular time steps. So you can see these arrows, and while decoding, this particular layer is going to have input on what initial word vectors, initial states should be considered while decoding the context vector, and what should be softmax gives us probabilities, right? So absolutely, in this case, in this visual case, this particular word and this particular word are more important than these two words, just for example. So the intermittent states of these two words will be multiplied by a softmax, will get a low probability, and then those weights will be considered or will make a negligible impact because of the low probability while decoding at a particular time step. So if this was confusing, let me try to summarize again. Basically what we are trying to learn is, given the intermittent states, along with a contextual state at the end of the encoding part. We are also trying to learn that what intermediate steps are important by what percentage in the decoder side, onto the decoder side. So, which in turn tells us while decoding how much attention I need to pay to what word, right? All the words need not get the same attention from the decoder. I have a context vector and I know while decoding how much attention I should pay to each particular word. And that is an extremely interesting concept, but that solves our problem of all the words having pretty much the same attention. So finally coming to BERT. Okay, BERT is a language model. Language model is, we get a corpus, we try to train a model with an objective function to, in a semi-supervised way, to learn the language. Okay, basically to understand the corpus and try to convert language into vectors, right? I mean, we used a very similar concept in word to vec. So Elmo again was a language model. It was trained over a corpus to give words in a sentence defined vector. Okay, so BERT is similar, a huge but still similar language model. So BERT was like trained on, I think, the entire Wikipedia corpus by Google. This is a Google Labs initiative. Um, the objective function in BERT was, they had two functions: next word prediction or next sentence prediction. So, or rather than next word, I should say masked word. Okay. So for example, I have a big corpus and I have to train my language model. Okay. So I would get a sentence and I would mask a word. And given the sentence with a masked word, the objective function of BERT training is to guess or train to find the vector of that particular word. Okay, straightforward, or maybe not so much. So what BERT essentially is, from the encoder decoder model which we looked at, BERT is encoder. BERT is trying to learn the language in order to code very efficiently. Okay, so if we pass a sentence to a readily trained BERT model, it is going to give me a sentence vector. Okay, so many sentences are passed through the model, through the training phase, which has multiple layers and which have multiple transformer blocks, and the task is to identify the masked word, and in such process the language is learned. Now attention is used in this. Okay, every layer has 12 attention mechanisms. So like on the previous slide, we saw that there was one attention mechanism. Not to overload that particular attention mechanism, there are different attention heads, like here, multi-headed attention, working together in tandem to learn where to pay more attention. So, it just does not get redundant. Okay. So an encoder is working here to, with the objective function, to find the masked word, and is getting trained in every repetition to better its prediction using multiple attention heads. Okay, using multiple attention mechanisms. So I'm not calling attention, the concept is not absolutely similar here, because this is self-attention and the attention we were looking at on the previous side was Badanu's attention. So they are, the basic concept is the same, but they are, mathematically different models. So, that can be a topic completely altogether for a different discussion. But here attention heads are used, multiple attention heads are used, and they are feeding on to different BERT layers. Okay, so one transformer is trying to guess the word with different attention heads. Same is repeated again, same is repeated again, same is repeated again n number of times, and then finally we get the sentence vector out here. So that is, BERT is trying to encode the sentence and learn with the objective function of missing word. Okay, so thus BERT is very efficient in fantastically encoding sentences, which has a lot of context, which has a lot of contextual information embedded. So, the vector we get out of BERT is really going to be rich. And once we get a rich vector, a lot can be done with that. And I think one thing I probably missed explaining here is there is also positional encoding. So position of the word, where the word is in the sentence, is also fed to the network. So the network will understand that first word is missing, second word is missing, or nth word is missing, and so on and so forth when it is trying to learn the language. So in short, this was BERT. Probably this deserves another talk and another presentation on the inner workings of BERT, and possibly a demo as well. But I think just to keep it short, I would end it here, and I hope you guys enjoyed the journey from classical NLP to BERT, which is transformer model. And I really hope Hugging Face is a library where BERT models are available. I would recommend each of you to go on to Hugging Face. You can easily download the models and try to play with it, and that can help you in understanding how BERT is working. I guess has been a really long presentation, so I'll just be done here. And if you have any questions, if you have any suggestions, if you have any comments, I'm on Slack, please ping me. And if you have any questions, if you want to email me, you can email me on shngodbole@icloud.com. Thank you.